Hi everyone. This is the Dr. S. Venkateswarlu, working as a professor of EC at IARE, Hyderabad. Today we are discussing about energy and power signals. Energy and power signals with it is most important for related all streams, especially here digital signal processing. It is very much useful in energy and power signal for estimating all signals and systems and so on. Energy signal, we know that the signal with finite energy and zero power is called energy signal. That is followed by, for any signal, we can represent in terms of the mathematical notation, 0 less than E less than infinity, and the power P is equal to 0. Signal energy of the signal is defined as the area under the square of the magnitude of the particular signal. Okay, here the units of the signal energy depends on the unit of the signal. Okay, with this, the signal energy of the signal is defined as the area under the square of the magnitude of the particular signal. The unit of the signal energy depends on the unit of the signal. We can consider mathematically Ex, where Ex is equal to integral minus infinity to plus infinity on x of t square into dt. So that energy and power signals, coming to this all power signal, some signals have infinite signal energy. In that case, it more convenient to deal with average signal power. So for power signals, 0 less than P less than infinity and E is equal to infinity. Okay. Average power of the signal is given by Px is equal to limit t tends to infinity 1 by capital T into integral minus capital T by 2 to t by 2 mod x of t square into dt. So mathematically we will represent energy as well as power signal like this. By using this all mathematical analysis, you can analyze that all. So what the status or how we are utilizing this, the energy and power signals. Okay. For a periodic signal, we know that all periodic signal, it is followed by x of t. The average signal is power is the particular power is Px is equal to 1 by 1 by t integral t mod x of t square into dt. Here in this case, the t is any period of the signal. Okay, the periodic signal are generally power signal. You know that. But in this, that energy and power signals we will estimate for the purpose for a periodic signal x of t. The average signal power is Px is 1 by t integral t mod x of t square into dt. Okay. Coming to the signal energy and power for discrete time signal. A discrete time signal with finite energy and zero power is called energy signal. But here we are talking about discrete time. In terms of discrete time signal, the signal energy and power for discrete time signal, how it is varies, how we are recognizing, how we are defining this signal energy and power for discrete time signal. For that, a discrete time signal with finite energy and zero power is called energy signal. That is, for energy signal, 0 less than E less than infinity and P is equal to 0. The signal energy of a for a discrete time DTS, discrete time signal, it is followed by x of n. You know that other day. Discrete time signal x of n. If it is x of t or x of t is the continuous time signal. Continuous time signal, here it is, this is nothing but DTS, discrete time signal. Okay, with this, the discrete time signal, what happens here, the signal energy of a for a discrete time signal, x of n is easily can represent what you call in terms of a ex in is equal to the summation n is equal to minus infinity plus infinity mod x of n, that is dts square. So the signal energy of a discrete time signal you can represent in terms of mathematical expression. Okay. Yeah. The average signal power of the discrete time power signal, it is followed by x of n, is mathematically it is represented px is equal to limit n tends to infinity 1 by 2n into summation small n is equal to minus capital N to n minus 1 mod x of n, the dts, discrete time signal. Here it is specified that discrete time signal square. Okay, so for a periodic what do you call the periodic signal x of n, the periodic signal for a periodic signal x of n, the average signal power is px is equal to 1 by n, the summation n is equal to n, the x of mod x of n, that is dts square. Okay, this, the notation, the summation n is equal to capital N means the sum of over any set of consecutive n's exactly capital N is length. Like this, you are right to specify that the average signal power of a DTS, or you can consider the discrete time power signal x of n is like this. For a periodic signal x of n, the average signal power is px. Okay, with this we write to represent this all power and signal. So it is somewhat interlinked with this system. You can consider it a system. The system processes input signals to produce an output signal. The system is followed by input section is the input, output section is the output. In terms of that, system is can process from input to output. The system processes input signals to produce an output signal. The system is a combination of elements that manipulates one or more signals to accomplish the functions to produce some output. Maybe that may be expected output response or output. Okay, input signal, we have to consider this input signal like this. System is followed by this one, and output we will expect. This is going to system process input signals to produce an output signal. So the system is a combination of the elements that manipulates one or more signals to accomplish the function to produce some output. Okay, examples of the systems. The circuit involving the capacitor can be viewed as a system that transforms the source voltage. You can consider the signal to the voltage as a signal across the capacitor. This is related to the circuit involving. The circuit is involving the capacitor condenser. It is going to be what we call passive component. Using this particular passive component can be viewed as a system that transforms the source voltage to the voltage across the capacitor. Yeah, coming to the communication system. In communication system is generally composed of three subsystems: the transmitter, the channel, and the receiver. Yeah, the channel typically attenuates and adds noise to the transmitted signal, which must be processed by the receiver. Okay, so with this, we will consider that biomedical system resulting in the biomedical signal processing and control systems. So, like this, there's an example of this particular fundamental aspect of the system. Okay, next consider one more example related to the system. Consider an RL series circuit using the first order equation to represent using this particular circuit diagram R and L. Okay, so both are considered in R and L. This R and L. Okay, consider an RL series circuit using the first order equation. Using this first order equation, where VL of t is equal to L into di of t by dt. Within this, VL of t is identified. Next, from that circuit, where V of t, if you try to calculate the V of t, where V of t is equal to what you call VR plus VL of t. VR plus what you call VL of t. Okay, it is where that V of t is equal to VR plus VL of t is equal to I of t into R, like in terms of V equal to IR. Okay, that V equal to, here it is, where V is equal to VR plus VL of t, that V is equal to I into R. Okay, that means I of t into R plus that what do you call that L into di of t by dt. Okay. So now coming to the mathematical model of the continuous systems. Most continuous time systems, because of we are considering that our system, just now we have verified that the system, but here in terms of the continuous system, what are the mathematical model or mathematical notations are involved based on this particular signal. The signal may be continuous signal. Most continuous time signals represents how continuous signal are transformed via differential equations. Example, RC circuit. Yeah, we can indicate system indicates car velocity. Yeah, it will indicate the system indicating the car velocity. So if you are the most continuous time system represents how continuous signal are transformed via differential equations. Construct RC circuit. By using this RC circuit, we should write that all mathematically. Mathematical modeling. D into Vc of t by dt plus 1 by RC into Vc of t is equal to 1 by RC into Vs of t. Okay. Now, system indicating the car velocity, m into dv of t by dt plus rho v of t is equal to f of t. So, under this mathematical modeling of the DTS, most discrete time systems represents how discrete signals are transformed via difference equations. Okay, so like best example is bank account, discrete car velocity system. But consider the discrete time system represents how discrete signals are transformed via difference equations. Yeah, and mathematically, that means in terms of mathematical modeling, it is followed by y of n is equal to 1.01 into y of m minus 1 plus x of n. Okay, with this v of n minus m by m plus rho delta into v of n minus 1 is equal to delta by m plus rho delta into fn. Okay, so the most discrete time systems represents discrete signals are transformed via difference equations. With this order of the system, we would consider the order of the system. Order of the continuous system is the highest power of the derived association or associated with the output in the differential equation. It is followed by m into dv of t by dt plus rho into v of t is equal to what you call f of t. The order of the above system is 1. Okay, the time. So order of the discrete time system is in highest number in the difference equation by which the output is delayed. So how it is delayed really under mathematical notation, mathematical modeling, or in terms of the manual operations that we will observe. Okay, with this order of the discrete time system in the highest number in the difference equation by which the output is delayed, it is followed by y of n is equal to 1.01 y of n minus 1 plus x of n. Okay, so the order of the above system is 1. Okay, easily can verify that all how it is order of the system is various. Now come to the interconnected system. Interconnected system is followed by parallel or serial may be cascaded, or we can consider feedback. Yeah, these are the interconnected systems. Okay, so consider that each and every one like parallel, serial and feedback. Okay, like this the parallel where x of t is the input, output we have to verify that y of t is equal to the operator t of x of t. Come to the serial or serial or cascade. So same values, here it is x of t is fed to the particular system. The output response y of n is equal to t of x of t. Now the serial or cascaded x1 of t, x2 of t and x3 of t with this one somewhere, and we will expect that y of t is equal to x1 of t plus x2 of t plus x of 3. Okay, so it will represent that all system related to interconnected. Okay, next come to the feedback where x1 of t, x2 of t connected with this one, and y of t we will try to verify that y of t is equal to x1 of t into x2 of t. That x2 is given to the feedback. Okay. So like this interconnected system will be appeared by using the mathematical notation like parallel, serial and feedback. After that, how it is interconnected system, what are the input variation and output variations, we will verify. Okay, examples of this interconnected system. Okay, so consider the following the systems with the 4 subsystems. Okay, the 4 subsystems like this. X1 is connected with 1 and 2, the output response of 1 y1 of t, the y2 of t. It is given to that. After that, we will try to verify that y3 of t. It is given to the third system. Output response is y4 of t. So after that, there is what you call the 4. Finally, we will try to verify the output response. So how many systems are our subsystems? Subsystem 1, 2, subsystem 3, subsystems 4. Interconnected system, how it is interconnected? The systems are available, first, second, third, fourth subsystems with the 4 subsystems. So what are the input level and output variations? How it is connected? So it is an interconnected system with a system with 4 subsystems. Each subsystem transforms its input signal. Okay, each subsystem transforms its input signal. The results will be like y3 of we are trying to consider that one output response here y1 of t, one more y2 of t, After that, we will try to verify the y3 of t, where y3 of t is equal to y1 y1 of t plus y2 of t is equal to what you call the t1. Okay, so like t1 of x of t plus t2 x2 of t. Similarly, now we need to verify that output response of y4 of t, where y4 of t is equal to t3 into t3 into y3 of t here. T3 into y3 of t is equal to t3 into t1 of x of t plus t2 of x of t. So this is the right to connect the calculate that subsystems, 4 subsystems. Here one is y1 of t and y2 of t, y3 of t and y4 of t. Final outcome is y of t. Therefore, that y of t is equal to y4 of t y into y5 of t is equal to t3 of t1 of x of t, t2 x of t into t4 of x of t. Like this, mathematically we have to verify. Next, come to the feedback used in the automatic control. E of t is equal to x of t minus y3 of t is equal to x of t minus t3 of y of t. So here we are to calculate the output response of this. Y of t is equal to t2 of m of t is equal to t2 of t1 into e of t. So we are going substituting these values t2 and in place of t2 value of which subsystem is involved here. That's why the t2 y of t, where y of t is equal to t2 into t1 of x of t minus y3 of t is also equal to t2 of t1 of x of t minus t3 of y2 of t, y of t. Okay, that is the automatic control. It is reflected that feedback. So it is also equal to t2 of t1 of x of t minus t3 of y2 of t. Like this, you are to verify that their input is x of t. It is given to this. We will expect that e of t, the control subsystem controller, and one more subsystem plant. The third subsystem is the sensor. Like this, easily can ready to calculate that e of t. System it is observed. Similarly, m of t also ready to calculate with the help of the controller subsystem 1. It is given to the plant. Subsystem 2, ready to verify that y of t is verifying, ready to calculate. It is some error or it is given to the feedback. The subsystem 3 is followed by sensor. Okay, sensor output will export the y3 of t. Again, it is given to that. Finally, what you call using automatic control system, we will verify in mathematical modeling. Okay, with reference to this order, directly we can focus on these types of systems: causal and anticausal system, and linear and nonlinear system, time variant and time invariant system, stable or unstable, static and dynamic, what you call invertible and inverse systems. Okay, now coming to the one by one. These are the major popular systems. What you call 6 popular systems are available for evaluating the DSP, digital signal processing, either in terms of the DTS or CTS. We will see one by one. Causal or casual and anticausal systems. So causal system, a system is said to be casual or causal if the present value of the output signal depends only on the present and or past value of the input. input signal. Okay, best example is where y of n, because of we are talking about the DTS. Y of n is equal to x of n plus 1 by 2 x of n minus 1. Next, anticausal system. Here, the system is said to be anticausal if the present value of the output signal depends only on the future values of the input signal. Okay, this. Okay, so best example is you can represent in mathematical notation. Y of n is equal to x of n plus 1 plus 1 by 2 x of n minus 1. Now coming to the next system, linear and nonlinear system. Okay, a system is said to be a linear if they satisfy the principle of superposition. For checking the linearity of the given system, firstly we check the response due to the linear combination of the inputs. Then we combine the two outputs linearly in the same manner as the input, and the inputs are combined and again total response is checked. Okay, so if response in step 2 and step 3 are the same, the system is linear, otherwise it is not. It is non-linear. Okay, time invariant and time variant systems. A system is said to be a time invariant if time delay or time advance of the input signal leads to a identical time shift in the output signal. Okay, so usually can represent mathematically y of t is equal to h of x of t minus t naught is also equal to h of s t naught into x of t is equal to h into s power t naught because t0 into x of t. Okay, the time the shift is y of y naught of t is equal to s power t naught y of t. Okay, that is also equal to what you call s t0 of h of x of t is equal to s power t0 into h into x of t. Okay, so like this we are going to verify that the time invariant time variant system, time invariant and time variant systems. So theoretically and mathematically, right, to verify that time variant, time invariant system. Okay, now coming to these stable and unstable systems. The system is said to be a bounded input, bounded output, BIBO stable if every bounded input result in the bounded output, that is it is followed by in terms of this y of n is equal to 1 by 3 into x of n plus x of n minus 1 plus x of n minus 2. Okay, so with this, now we are representing this example y of n. A system is said to be a bounded input, bounded output stable. You can consider that what you call BIBO stable. If every bounded inputs results in a bounded output. Okay, like this, that mathematically it is represented of t x of t what you call less than or equal to mx less than infinity t y of t less than or equal to m of xy less than infinity. Okay, so the time easily can calculate that y of n is equal to 1 by 3 x of n plus x of n minus 1 x of n minus 2 is less than or equal to 1 by 3 x of 1 by 3 x of n plus x of n minus 1 plus x of n minus 2. It should be used that are mod if there is any negative values. So use this 1 by 3rd 1 by 3 into x of n plus x of n minus 1, x of n minus 2, x of n minus 3, and so on. So less than or equal to 1 by 3 mx plus mx is also equal to mx. Okay. With this, what are the stable and unstable system? Example. Best example is the system represented by y of t is equal to a into x of t is unstable when what you call a greater than 1. Okay. So reason is, let us assume the x of t, where this x of t is equal to u of t. Okay. Then at every instant u of t will keep on what you call multiplying with this a, and hence it will not be bounded. Okay. Easily you can represent by using this particular system. Next, static and dynamic systems. A static system is memoryless system if it has no storage device and its output signal depends only on present value of the input signal. Example. Okay, that example is represented what you call where I of t is equal to 1 by r into p of t. Yeah, coming to this, a dynamic system possesses memory if it has storage device. The system is said to be possesses memory if its output signal depends on past values and future values of the input signal. Using this dynamic system, that static system is, we can consider that what you call where I of t is equal to what you call 1 by r into what you call v of t. Okay, if it is dynamic system possesses memory if it has storage device, but consider that where I of t is equal to 1 by L into what you call integral plus minus infinity to plus infinity. Okay, v into tau into d tau. Okay, or if it is here in this case, if it is the static system, it is followed by I of t, where this I of t is equal to 1 by r, that reciprocal of the resistor 1 by r into v of t. Okay, like this, that system. A system is said to possess memory if its output signal depends on the past value and future values of the input signal. So that time we write to verify that y of n. DTS, output response, discrete time output response, it is followed by y of n, where y of n is equal to what you call that x of n, okay, plus x of n minus 1, okay, plus x of n minus 2, and so on, because of it possesses the memory if its output signal depends on past value and future values of the input signal. Now coming to the invertible and inverse systems. If a system is invertible, it has an inverse system. Okay. Yeah, we have to consider this all. If the system is invertible system, it has an inverse system. Consider this system. The system is, particular system is, input is x of t. You can consider where it is CTS, continuous time signal. It is given to the system. System output will export that y of t. That y of t is fed to the inverse of the system we will expect that all x of t. If the system is invertible, it has an inverse system. Okay, like in mathematical we will represent that all y of t is equal to 2 into x of t. Okay, it is in terms of the invertible. Here the system is invertible as it has inverse system. That is, for any x of t, we get a distinct output of y of t. Thus, the system must have an inverse. The system must have an inverse. Okay, where x of t is equal to, here you can represent it mathematically. Here it is x of t, where x of t is equal to 1 by 2 and y of t is equal to, where y of t is equal to z of t. Z of t. Okay, so that input is here, system multiplier x of t. We will expect output response is y of t is equal to 2 into x of t. It is given to this inverse system, the divider, we will expect little x of t. Okay, like this, try to verify that invertible and non-invertible. Present we are concentrating on invertible. The system is invertible as an inverse system. The system is invertible as it has inverse system. Easily can analyze by using the consider the multiplier and the divider. Multiplier and divider. Input is x of t, where output is x of t. Next, come to the LTA system. Already we have seen that LTA system, but with reference to that all, the LTA systems are completely characterized by its unit sample response, linear time invariant system. The output of any linear time invariant system is a convolution of the input signal with the unit impulse response, that is what we can represent the y of n is equal to x of n convolved with h of n. X of n convolution with h of n. So finally that y of n is equal to the summation k equal to minus infinity plus infinity x of k into h of n minus k. Okay. Now coming to the useful properties of discrete time, linear time invariant system. The popular property is causality and stability. Okay, if it is causality, h of n is equal to 0 if n less than 0. Coming to the stability, the summation k equal to minus infinity to plus infinity, h of k mod h of k is k less than infinity. Okay, here bounded input to bounded output or bounded output to bounded input. Okay, we will consider for x of mod x of n less than or equal to x maximum less than infinity. Okay, where y of n is equal to the mod of the summation k equal to minus infinity plus infinity x of k into h of n minus k less than or equal to x maximum, the summation k equal to minus infinity plus infinity h of n minus k. Okay, like this, we need to represent that all x of n and if it is x of n mod x of n, okay, less than or equal to x maximum. Okay, x maximum less than infinity. Yeah, similarly that y of n, like here y of n, okay, that y of n is equal to, so mod the summation, the summation k equal to minus infinity to plus infinity x of k, okay, that x of k into h into n minus k, n minus k with the mod is also less than or equal to, where less than or equal to, or you can consider this less than or equal to the mod, the summation, okay, summation where k equal to minus infinity to plus infinity, okay, h of n minus k, h of n minus k with this, what do you call, you can decide the factor. So we can consider this is the bounded input and bounded output, which will be useful properties based on discrete time, linear time system with the, what do you call, casual, causality and stability. Now coming to this, what do you call, time domain analysis of discrete DTS. Time domain analysis of DTS, discrete time system. The time domain analysis of discrete time systems. You have to verify that discrete time system equations first mathematically, and E operator, response of the linear time, response of linear discrete time system, linear discrete time systems, useful signal operations, response of linear discrete time systems, what are the response. After that we'll verify that what do you call, zero input, zero state response of the convolution sum. Of that try to verify the graphical procedure for the convolution sum, and classical solution of the linear difference equation we have to verify. This is under the time domain analysis of discrete time systems. It is all purely based on the DTS. It's all are evaluated by using DTS, discrete time signals. The discrete time signal is, it is specified x of n, or we can consider that x of n like this. With reference to this discrete time signal, how it is evaluated in what you call time domain analysis of discrete time with reference to discrete time system, a mathematical notation, E operator, response of the linear discrete time system, useful signal operations are either independent or dependent, response of linear discrete time systems, after response, zero input and zero state response, how it is varies. Based on this all analysis, the convolution sum will calculate in mathematically and practically. After that, the graphical procedure for the convolution sum. Finally, classical solution of linear difference equation will be investigated. After that, we are going to satisfy this time domain analysis of DTS, discrete time systems. Okay, time domain analysis of discrete time system, DTS. Okay, here discrete time system equations, advanced operator form. By using the advanced operator form, it is followed by y of k plus 1, k plus n plus an minus 1 into y of k plus n minus 1 plus and so on. a1 y of k plus 1, a0, here it is a0 y of k, bm f of k plus m plus bm minus 1 f of k plus m minus 1 and so on. Like this, the discrete time system equations, it is advanced operator form, or operator forms are depending like this mathematical notation. The left hand side of this form, it consists of the output at instants. Okay, like k plus n, k plus n minus 1, k plus n minus 2, k plus n minus 3 and so on. The right hand side of the equation, it consists of the input at instants, like k plus m, k plus m minus 1, k plus m minus 2, k plus m minus 3, and so on. Okay, the condition that the above system is causal is m less than m. M less than or equal to m. Okay, the system is causal or system is casual. Okay, so for a general causal case or general casual case, okay, so where if it is what do you call m is equal to n. But if it is causal is where m less than or equal to n, less than or equal to n. For a general causal case, if m is equal to n, okay, after that the above system can be expressed as, okay, y of same, that y of here like this, that y of n plus an minus 1 into y of k plus n minus 1, okay, and so on, a1 y of k plus 1 plus a0 y of k is equal to, so it is varies, bn of, okay, here it is bn of k plus n plus bn minus 1 f of k plus n minus 1 plus and so on plus b1 f of k plus 1 plus b0 f of k. Okay, like this you are right to represent what you call the time domain analysis of discrete time systems with this. The delay operator form in case where m is equal to n. Normally we know that m less than, that causal is m less than or equal to n, isn't it? But this case where it is, in case of m is equal to n, we can replace k by k minus n throughout the equation. Such replacement yields the delay operator form. This is the most important replacement. Replacement yields the delay operator form. Of that, in place of that, k by k minus 1 throughout the system, replacement yields the delay operator form. That means y of k is equal to y of k plus an minus 1, y of k minus 1 plus and so on plus a1 y of k minus 1 plus 1 and so on plus a0 y of k minus 1 is also equal to that, what you call that bn f of what you call bn f of k plus the bn what do you call, okay, bn minus 1, okay, with f of k minus 1, okay, k minus 1 plus and so on, okay, plus b1 into f of k minus n plus 1 plus what you call b naught into f of k minus 1. Okay, like this, from the above delay operator form, y of k plus an minus 1 y of k minus 1 plus and so on plus a1 y of k minus n plus 1 plus a0 y of k minus n is equal to what you call, okay, bn f of k plus bn what you call f of bn minus 1 f of k minus 1 plus and so on plus b1 f of k minus n plus 1 b0 f of k f of k minus 1. Okay, it can be expressed as y of k y of k is equal to minus an minus 1, y of k minus 1 minus an, here it is an, okay, it is specified that an minus 2 y of k minus 2, k minus 2 minus and so on minus a naught y of k minus 1 k minus n plus bn f of k plus bn minus 1 f of what you call k minus 1 plus and so on. So here it is there are the past and n values of the output. Okay, that is y of, that is nothing but what you call y of k minus 1, okay, and y of k minus 2 and so on, y of k minus up to n. So the first n values of the input, what you call n value of the input, it is f of k minus 1, f of k minus 2, f of k minus 3, f of k minus 4 and so on, f of k minus n, and the present value of the input f of k. So based on this delay operator form is written what you call mathematical model will applicable in case where m is equal to n. If it is m less than or equal to n, already it is decided what you call it is the causal or causal system. Okay, so like this try to verify that all DTS with reference to all the systems. These you can what you call observe this, the output response is either it is depending upon all delayed operator form or before and above. In case if the causal where m less than or equal to n or m is equal to n, how it is the way is the system. Okay.
Like, share and subscribe. Hit the bell icon for more updates.